Yeah, thank you, Sandra. Oh, not Monday. Gosh, I keep saying Monday. For Tuesday. So those 3 videos for Tuesday. Try to watch those 3 videos for Tuesday, and then Tuesday to Thursday we will watch the rest of chapter 4 of 4.4, and then a little bit of 4.6. So yeah, I keep forgetting we're not on the Monday through Thursday schedule. So for Tuesday. Any questions? Any other questions about logistics and timing and what to be working on and what's due? Okay, I'm not seeing any. Let me see here. And I'll make sure nobody else is waiting to get in. Nope, I don't think so. Okay, so I have the textbook up here, and I thought we could take some time and go over any homework questions you had from 4.2 and 4.3, because we're going to have our quiz on those today. So who would like to get us started? Maybe since I have 4.2 open, let's start there. So who has a question from 4.2? My list here too. If we don't have any questions, I have some examples we can do too. So, all right, we have 4.271 from Chantel, and then Lorenzo, I see your hand. We'll do yours next. So 71, quick scroll. Wow, that's a long section. 71. Okay. Oh, I feel like didn't we talk about this one? I think we did. Maybe we just didn't finish it, or 61. Okay, 61. I was like, wait a minute, that looks really familiar. 61. Okay, so we did 61 too. I have proof. Oh, but can I find?
No, we did. I was looking at 4.3. I'm sorry.
Okay, all right. So we'll come back to 4.3. All right. Lorenzo, you have a 4.2 question? Trying to unmute you. I can't unmute you, Lorenzo. I don't know if you don't have audio.
Oh,
there you go. Go ahead.
Yeah. I think it was 51.
X squared over x minus 1.
Yeah, was that one of our homework questions?
Let me take a look here. 51 from 4.2 was indeed on the list. So
Okay,
let's take a
then,
look
yeah,
at it. Yeah, let's take a look at it. And the directions here, we're trying to find the absolute maximum value and absolute minimum value. Okay, so 4.9 homework questions, trying to be more organized here. Okay. So let's take a look. X squared over x minus 1 on the interval -1 to 1/2. Okay, so first of all, one thing you can do is check the left endpoint and see what that function value is. Well, we're going to need that. -1 squared over -1 minus 1. 1 over -2, that's -1/2. And then we'll check the right endpoint, f of 1/2. 1/2 squared over 1/2 minus 1. 1/4 over -1/2. And let's see here, that's 1/4 times -2 over 1, so -1/2. Oh, so they are the same. So at the endpoints, it's -1/2. It's -1/2 at the endpoints. And then we need to look for critical points. We need to look for critical points. Are there any horizontal tangent lines or any cusps where the derivative does not exist? So let's take the derivative. We'll just do quotient rule. The only other option would be to write it as x squared times x minus 1 to the negative first, and then do product rule. I think that actually would be a bad idea. I think it's better to have one fraction. And so just the quotient rule. So that would be x minus 1 times 2x minus x squared times 1 all over x minus 1 squared. And we'll clean that up a little bit. 2x squared minus 2x minus x squared over x minus 1 squared. And let's see here, x squared minus 2x over x minus 1 squared. Get a little extra space here. Okay, so we are looking for critical numbers, and that can occur two different places. It could be when the derivative is 0, or when the derivative does not exist. Now, to be clear, that's when the derivative doesn't exist. Like, we're not going to worry about vertical asymptotes for this context because you can't have a minimum value at a vertical asymptote. So my point is, for that one, yeah, at x equal 1, the derivative doesn't exist, but the function doesn't exist at 1 either. And so we're not going to try to evaluate f at 1 because the function doesn't exist there. But we are interested where the derivative is 0. And the key when you have a fraction like this is you want to set the numerator equal to 0. And just a little basic algebra, factor out an x. We get x is equal to 0 and 2. I'm actually going to ignore one of those. Totally ignore it. And just cross it off. Does anyone know which one I'm just going to ignore and why?
One, x equals 1, because it's not in the domain of f of x.
That's true. So I was thinking in my head of the 0 and 2. Of the 0 and 2, of those two, I'm actually also going to cross off one of those.
2.
The 2.
The 2, and I think that was Lorenzo who said first. What are you thinking, Lorenzo? Why the 2?
Because it's also out of the domain.
Yeah, it's in the domain of the function, but not in our domain that we are interested in. You're exactly right. It's not in the bracket -1 to 1/2. Okay, so now we just test f at our 0, and that was 0 squared over 0 minus 1, going back to the original function. 0 squared over 0 minus 1. And that's 0 over -1, so that's 0. So if we summarize, we have f of the left endpoint was -1/2. F of the right endpoint was also -1/2. And then f at our critical number was 0. And so it looks like the absolute minimum is -1/2, and the absolute maximum is 0. Does that help on that one, Lorenzo?
Yeah,
Maybe.
it does.
Let me, let's graph it. Nice way to confirm. Y equals x squared divided by x minus 1. And we're just going to look, I'm going to do, you can do this, was it -1 less than or equal to x less than or equal to 1/2. So it's kind of nice. You can like just graph a section of it, and there you go. Whoa, whoa, sorry. I meant to zoom in just over here, and you can see the endpoints, -1/2, are the same at the endpoints, and the maximum is at 0. So confirms what we got algebraically or analytically there. Good. All right. Any other 4.2 questions while we are in 4.2? Where did those go? Oh, I should have stayed there. They are over here. Any other 4.2 questions? Okay, I'm not seeing any more. So let's do Chantel's 4.3. But the ones you were wondering about are not on the 4.3 list. The 61 and 71.
No, it was 53 is the one that I had circled. I just had the wrong homework list out. I was counting 3 back from the end, and there's the wrong list.
Okay, all right. So 53 in 4.3. So let me get over to 4.3. Okay. So Rolle's theorem and mean value theorem. 53. All right. And we'll come over here. We're going to show that this function is increasing. So did you have any questions about, any ideas about getting started on this one, Chantal?
Well, I was trying to do the factoring, and I set up the number line the way that Miss Sugar did it.
Sugar, yep.
So it says, okay, not increasing on any interviewer containing x is -1. So it was like when I was doing it, I don't know if I was doing the wrong, maybe different values than I was supposed to on the number line.
Well, let's take a look.
Derivative of it.
Yeah, I think what you're saying is you're trying to make like a number line for the derivative. And then if it's always increasing, what should be true about the derivative? If the function is increasing, what should be true about the derivative?
It's positive.
Greater than 0.
Positive, greater than 0, right, Savante, right, Chantal? Should be greater than 0, should be positive. So let's see if that's true. And actually, it says show that it's always increasing. So it must be true. We're just trying to show that it's true. So the derivative, another quotient rule, x plus 1 times 1 minus x times 1 over x plus 1 squared. We get x plus 1 minus x over x plus 1 squared. Oh, that's kind of boring. We get 1 over x plus 1 squared. Boring is good because then you don't have a lot of critical numbers to find. In fact, if we try to find where this one has horizontal tangent lines, like set the derivative equal to 0, that's never true. There are no horizontal tangent lines. But the derivative f prime of x does not exist at x equal -1, which is also the vertical asymptote of the original function. So the only really interesting split point on your number line here for the derivative chart is -1, which is the vertical asymptote. So what you're going to do, and it sounds like you did this, Chantal, maybe just something wasn't quite working right. What you're going to do is you're just going to pick any number less than -1, like -10 or something, and then any number bigger than -1, like 0, and test those in the derivative. We're going to test -10, and you don't have to use these two numbers, just any number on either side. You're going to test -10 and 0 in f prime of x. And you don't really care what the number is. You just care, is it positive or negative? And in fact, we don't really need to test it because it's 1 over x plus 1 squared. The fact that the denominator is squared means it can never be negative. So it doesn't matter what numbers we put in there. When we square it, it's definitely going to be positive. And when we put in 0, it doesn't matter what numbers we put in because we're squaring the denominator, so it's always going to be positive. Yeah, Albert?
You only plug it back into the derivative, not the original function?
Correct, because I'm trying to determine is the function increasing or decreasing there, and the derivative is what tells me that. The derivative is what tells me whether it's increasing or decreasing.
Yeah, I plugged it back into the original function, so like all my answers were
Right.
coming up wrong, and I was trying to figure out what am I doing wrong. So yeah, that helps.
Yep. So that's the key. Increasing or decreasing, it's the derivative that tells you that. The derivative tells you whether or not your function is increasing or decreasing. So what I would do to finish my chart is I would say, well, it's positive over here, so that means the function is increasing. It's positive over here, so my function is increasing. So therefore, the function is always increasing, except at the vertical asymptote. And again, you can graph that, x over x plus 1, and you'll see that it is always increasing. You see that? Always increasing. Increasing on the left, vertical asymptote, increasing on the right of it. Always increasing. All right, great. Good question. Good one. Any other 4.3 questions? Any other
Can you go
4.45?
over 45?
45, certainly. This one I think is going to be a little more interesting. This is a little more interesting function. And let me see, we're supposed to determine where each function is increasing or decreasing. So similar. We're going to make a first derivative chart, except I think it'll be a little more interesting this time. Oop, too far, sorry. Okay. All right, let's find the derivative then. We'll need the product rule. The derivative of e to the x is e to the x times sine of x plus e to the x times the derivative of sine of x, which is cosine of x. And we want to set that equal to 0, and then also determine where it does not exist. In fact, e to the x, the domain is all real numbers. Sine of x, the domain is all real numbers. Cosine of x, the domain is all real numbers. So the derivative always exists. It's never undefined. But it should be equal to 0 on a couple of occasions. And so here's how we're going to do it. We're going to set this equation equal to 0. Let's set this expression equal to 0. There's an e to the x we can factor out. So there's two possibilities there. Either e to the x is equal to 0, or sine of x plus cosine of x is equal to 0.
E to the x is not equal to 0 ever.
Never. So that one, out. Yeah, e to the x is never equal to 0. That's correct.
Sine equals negative cosine x.
Yeah, that definitely is true. That is true. You can solve it a variety of ways. I like the graphs personally for me. If we graph those two, sine of x, and then negative cosine of x would be reflected, right? It would start down at -1 and then go up to +1 and then back down to -1. And you can see there's a couple of times where they're equal. You could also, if you know your unit circle, sine of x is the y coordinate, cosine of x is the x coordinate. So you're basically wondering, when are the two coordinates opposite signs? And so if you have your unit circle, you also know you also can look at, like, where would they be the same value but opposites?
Okay, so it doesn't just matter like sine is positive and cosine is negative. They're just opposite no matter what.
Correct. This is why this is really confusing here, and I'll get to you, Tvante. I think you had it pinpointed, so hold that thought. We always say negative. We say negative, and we say, oh, sine is negative cosine, but it's really the opposite. That's really what that means. So you're correct. It doesn't matter which one is negative and which one is positive. They just have to have the opposite sign. Yeah. Tvante, you were going to pick out you had said something about which quadrants?
Yeah, quadrant 2 and quadrant 4.
That's correct. Yep. Does anyone know the angles where they're the same value but opposite signs?
3 pi over 4, 7 pi over 4.
Yeah, yep, right. So 3 pi over 4, very good. and then 7 pi over 4. And you can see on the unit circle, the x and y would be the same values, but opposites there. And you can see that here on the graphs as well. So x is equal to 3 pi over 4 and 7 pi over 4. So we're going to do a number line like we did for Chantel's, except I'm not going to put arrows at the end because we're only looking at it from 0 to 2 pi. And so I'm going to mark 3 pi over 4 and 7 pi over 4. And we just need some test numbers in there. We need 3 test numbers. 1 left of 3 pi over 4, 1 between them, and then 1 to the right of that. So I don't know, what are some good test numbers? Anyone have any ideas?
Pi over 2.
Pi over 2 for the first interval, sounds good.
3 pi over 2.
3 pi over 2.
Oh,
And then
What
2
were we
pi.
going to say? I'm sorry, what were we going to say,
I was
Tavante?
gonna say, like, it really doesn't matter any number between those numbers.
Correct.
Okay.
Yep. Like you could use pi, you could use, I mean,
Right.
you could use 3
Mhm.
or 4, right? Because you could use your calculator. Yeah. So anything in there is fine.
Okay.
And then 2 pi, Christopher was saying 2 pi, it's technically an endpoint, but it's not a place where the derivative is 0. So the sign of it there will give us the information we need. So that is totally fine. The key here for our f prime of x, I'm going to write it as e to the x times sine of x plus cosine of x. See, the e to the x part is always positive. So all I really need is the sine minus plus the cosine to see if that's positive or negative. And you can use your calculator here if you want to. You shouldn't need to though. So sine of pi over 2 is, so this is whatever e to the pi over 2 is, and then sine of pi over 2 is 1, cosine of pi over 2 is 0, so that's positive in there. So it's increasing in that interval. 3 pi over 2, it's e to the 3 pi over 2. Sine of 3 pi over 2 will be negative 1, and then cosine of 3 pi over 2 will be 0, so that's negative. And then at 2 pi, e to the pi over, or sorry, e to the 2 pi, whatever that is, times, let's see, sine of 2 pi is 0, cosine of 2 pi is 1, so that's positive again. Are we supposed to determine where each function is increasing and where each function is decreasing? Okay, so answer, f is increasing on, let's see, 0 to 3 pi over 4, a parenthesis at 3 pi over 4, because it's a horizontal tangent line there. Technically, it is increasing at 0. It's hard because we didn't test there, but that wasn't a spot where the derivative was 0, so it is still increasing there. And then it's also increasing on the interval, not 7 pi over 4, but starting there to 2 pi. And then f is decreasing on the interval in the middle there, 3 pi over 4 to 7 pi over 4. I'm going to come back, but just quick again, use your tools at your disposal. Do a quick sketch. Y equals e to the x times sine of x, and we're just going to graph it from 0, sorry, x less than or equal to 2, and you can actually type in pi, and it kind of knows what you mean. And, whoa, it really, whoa, look at how, that's exponential growth there. It really, what? Whoa, it tips way down. That's crazy. That's wild. Can we change the x to go like negative 6 to 6? then we need to change the y to like something crazy. But you can see here's this peak. Oh, look, it even knows the peak is at 3 pi over 4. That's pretty cool. So Desmos is pretty smart, knows that peak. So increasing up to 3 pi over 4 and then decreasing. And then somewhere, wait, hey, there it is. That's going to be 7 pi over 4. Look at that. That's cool. And then increasing after 7 pi over 4. So another one, the graph kind of really reinforces our work. That's good. Are we good on that one, Christopher? Right. You might have stepped away. So that was a good question.
I forgot the space button.
It's all good. It's all good. Yeah. I never know who was actually there and listening, and people could be like, yep, I'm in, and then like walk away and I have no idea. It's okay. Any other questions from 4.3? Any other 4.3 questions?
Could you go over 37?
All right, let's find that one. This is another one, right? Increasing, decreasing. Yeah, okay. And this one has some funky algebra. Well, this one, I don't think it's quite as simple. It seems like an earlier one, so it should be easier, but I don't think it is. All right, product rule, 2/3 x to the negative 1/3 times x squared minus 4 plus x to the 2/3 times 2x. Ooh, boy. I think the way that I would do this one is I want to eventually set it equal to 0 and see if there's any places where the derivative is undefined. And I know I've got the negative exponent, so it's going to make some fractions. So I think I need to write it as a fraction and then try to combine them into a single term. I think that's how I would approach this one. So this would be 2 times x squared minus 4 over 3x to the 1/3 plus 2x to the 5/3. So the 3 was already in the denominator. The x to the negative 1/3 became x to the positive 1/3 in the denominator. And then the x squared minus 4 stayed in the numerator. And then the other one, it would be x to the first, which is 3/3 plus 2/3 gets me 5/3. So now what I want to do is I want to get a common denominator. So the denominator is 3x to the 1/3. So I know I need to multiply by 3 over 3, and then I'm going to multiply by x to the 1/3 over x to the 1/3 as well.
Could you have tried to factor out the x to the negative 1/3 and gone about it that way? Okay.
Yes, yes. I think that's a more advanced strategy, honestly. And I think that might lose more people, but that's totally appropriate, yes. I'm going to write this as 2x squared minus 8, if that's okay, and then plus 3x to the 1/3. They're both over 3x to the 1/3, and the other one becomes 6x squared. Because you have x to the 5/3 and x to the 1/3, and you add them together, you get x to the 6/3, which is x squared. Maybe not as bad as I thought. So you get 8x squared minus 8 over 3x to the 1/3. We did one step of calculus, and then the rest of this was algebra, but kind of non-trivial algebra. Any questions so far about either the derivative or the algebra steps that we did?
I'm still kind of confused how you get the 2x 2x to the 5/3.
Yeah, that's so x to the 2/3 times 2x. So that's where the 2 comes from. And then x is really x to the first. And so you're going to add those exponents, 2/3 plus 1. But 1 is 3/3, and so that's 2x to the 5/3.
Oh, okay, I see it.
Yeah. Just weird. We don't deal with fraction exponents very often, so it's a little, feels a little weird, but yeah. Okay, now we're looking for critical numbers because we're trying to find increasing and decreasing, just like we did for the previous one. So we need to see, is the derivative equal to 0, or does the derivative not exist anywhere? For setting the derivative equal to 0, this is a fraction, and fractions are only 0 when the numerator is 0. So we can just set 8x squared minus 8 equal to 0. But this one is a little interesting for when it doesn't exist. The derivative is not going to exist when the denominator is 0. And so we actually have something. This is the first one. We actually have something where the denominator, where the derivative can't exist. That one's easy. You can just say, well, x is 0. And you'll notice if you look back at the original function, that was not a problem in the original function. 0 is in the domain. This is in the domain of the function f. So there is a point there, actually. There is a point there, and we'll see it in the graph when we check our work, like always here. We'll see it in the graph, but it just, the derivative doesn't exist there. I don't know if you've looked at this one already or looked at these. Does anybody know what that means about the graph if it's in the domain, but the derivative doesn't exist there? You know what that looks like on the graph?
Even in a cusp or no?
Yes, you're right, Nick. It's a cusp. Yep. Yep. The other option is you could have a vertical tangent line, and I don't think that's what this one is. I think this one is a cusp. But there are some that have vertical tangent lines too. So it's either a cusp or a vertical tangent line. All right, so we're going to factor out an 8 here for the other one. We get x squared minus 1. So x squared is equal to 1. And don't forget that means 2 of them here. X is positive or negative 1. I'm going to rewrite our derivative here. 8x squared minus 8 over 3x to the 1/3. And then we're going to have a derivative chart. We have -1, 0, and 1. So we have 4 different intervals we're going to have to test.
-2.
Sure, sounds good.
-0.5. 0.5 and 2.
Sure, that's fine. Sounds good. Sometimes I'll even pick like really big ones on the edges, like -100 and +100. Just make it obvious. You don't really even need to do any math because it should be obvious. So the less work you have to do, the better for these. Let's see, 8 times -2 squared minus 8 over 3 times -2 to the 1/3. Hey, Sydney, we're working on number 37. 37? Yeah, 37 in 4.3. Let's see here. The numerator, see, I don't really care. I don't care what the number is. I just want to know whether it's positive or negative. The numerator, that's 4 times 8, 32 minus 8. That's definitely positive. The denominator, -2 to the 1/3. Is that going to be positive or negative? -2 to the 1/3.
Would it be negative?
It would be negative, yeah. Yeah, it would be negative. It's the cube root, so it's some negative number. So that means the whole thing is negative, so it's decreasing over there. Then at -1/2, 8 times -1/2 squared minus 8 over 3 times -1/2 to the 1/3. The numerator, let's see here, 1/4. 8 times 1/4 is 2. 2 minus 8, that's negative. The denominator is still negative, so that's actually positive in there. It's actually positive. And you can use your calculator for these and plug them in. Whatever you need to do is fine. I'm just lazy. I don't want to do all that work. And then I got to go below for +1/2. 8 times 1/2 squared minus 8 over 3 times 1/2 to the 1/3. The numerator is the same. It's -2, right? 1/2 squared is 1/4. 8 times 1/4 is 2. 2 minus 8 is negative 6. And then denominator, though, now is positive. So it's negative and decreasing. And then finally at 2, 8 times 2 squared minus 8 over 3 times 2 to the 1/3. Everything's positive here, positive over positive. So it's increasing. So I don't know if we need to write the intervals there, but it would be decreasing from negative infinity to negative 1 and from 0 to 1, and then increasing from negative 1 to 0 and 1 to infinity.
On the quiz, do you want us to write it all out of what's increasing and what's decreasing, or do you want us to just leave it at the number line?
Yes, I want you to write it out. Good question. Yeah, good question. So let's get in a good habit here and write it out. So we'll say f is increasing on the intervals from negative infinity to negative 1. You can even say union. Wait, no, it's not increasing there. It's increasing. I cut my table off. There we go. Increasing on the interval negative 1 to 0 and 1 to infinity. And decreasing on the interval, that's the negative infinity to negative 1 and 0 to 1. So you do want to state the intervals. Haley had a question?
Yes. Why are you using parentheses instead of brackets?
That's a good question. Does anyone know the answer to that? It's a really good question.
Is it because it's an open interval? It's not like we're not like closed looking in between the set numbers?
Yes, kind of. So why, does anyone know the difference between the bracket and the parenthesis? Right, the bracket, if I were to include 0 to 1, that means that we're including 0 and 1?
You mean at that point?
Correct.
And you put like -2, or you set the increasing value as -1 to 0, union 1 to infinity. It means like in the range of those numbers.
Right. And so the question is like, what about at 0? Is it increasing at 0? Right at 0.
Because the slope is 0, right?
Correct. No, not 0 there. That was close. That was one of the cusps. But right idea. Yeah. Yep. So you have to leave those out. And the negative 1 and 1, those are the zeros. So it has a horizontal tangent line and negative 1 and 1. So it's not increasing there. It's not increasing at those endpoints. Does that answer your question, Haley?
Yes.
Let's take a look at this one. I think always good to look at the graph. I got to remember the original equation. X to the 2/3 times x squared minus, I lost it already, 4. X to the 2/3. I guess we'll see if I did it right. Oh, we have our weird window. Oh, we need to like reset. Oh, all right. I'm just going to copy this and refresh because we had that weird window for that last function. Need to like just reload. There we go. Oh yeah, cool. Look at that. So here's our minimum. So decreasing to -1, increasing, and then there's your cusp, and then increase or decreasing up to 1, and then increasing after. Cool. See, I love the graphs. I think that's so helpful to see that visual and have it back up, hopefully back up what you thought. Now, you're not going to get any points if you just draw the graph and like, oh, look, it's decreasing from negative infinity to -1, 0 to 1. Sorry, that's not how it works. But it's a good way to reinforce.
You go back to the graph.
Yeah.
So would the 1 be a local min?
Yep.
Okay.
And actually, so you could say there's a local minimum at the point 1, -3, but it's also the absolute minimum of the function is -3.
Oh, okay.
Right? Because it's the lowest that it gets. Now, it happens twice, but it is the lowest that it gets.
And the
There's
local max will be 0.
Yep, the local maximum at that point, 0, 0. There is no absolute maximum because it continues up. So yeah, we call those local relative minimums. Yeah. Relative minimums, relative maximums. Yeah, good. Anything else on 37? These are some good examples that you were asking about, so this is good. I don't mind if we don't. If you look at, I uploaded some practice questions, but they're very similar. Find the absolute extrema. Show where it's increasing or decreasing. Oh, look, I picked, it must have been like the next one to Christopher's one. So we're doing examples really just like the ones I was going to do. So if we don't get to them, that's okay. Any other homework related questions? And if you came a little bit later, you can ask some 4.2 if you like. We did some of those already, but we could go back and do some of those.
39.
Still in 4.3?
Yes.
Absolute value. I feel like absolute value, or no, you're not 43. Sorry, 39. Absolute value seems like such an easy concept, like, oh, you just make stuff positive. But in calculus, it makes everything worse. Absolute values just seem to make everything worse. Oops, where'd it go? Okay, there we go. I will tell you how I do these. I'm not sure if it's the best way, but I don't know how to take a derivative with an absolute value. So I feel like I need to get rid of the absolute value. So here's the key for me. Say I have a different function and it is the absolute value, just the absolute value of x. And I want to write that without the absolute value. I have to do it in pieces. It has to become a piecewise function. See, if x is not negative, then the absolute value doesn't even need to be there. So I could just say this is x if x is greater than or equal to 0. I can just, you don't even, if the number is not negative, then the absolute value is totally redundant. What if x is negative though? What if say x is -6? How could we make it positive without an absolute value bar? What else could we do to make it positive?
Can you square it?
But that changes the value. So it makes it 36.
And then take the square root?
So you could, you're right. We could do that. We've done that, right? Oh, I'm forgetting about that strategy. So we've done that too. Do you remember doing that? The square root of x squared. So we could do that. We could do a chain rule. Maybe that would be best. Because here's what I'm thinking is, if x is -6, you just need the opposite of it. That makes it +6. And so you could do the opposite of x is +6. So the other thing you could do for an absolute value is you can do a piecewise function. But I think that might be harder here. Thank you for reminding me of that, Haley. I think that's probably the way to do this one a little bit easier, is to use the fact that the square root of x squared is the same as the absolute value. So let's see how miserable that looks. If we have x cubed plus 3 and we square it and we take the square root, we're going to have to do a double chain rule in the derivative here. Okay, it's all right, we can do that. I'm going to rewrite this as x cubed plus 3 squared to the 1/2. Now you might want to multiply those and just call it to the first, but the whole point is that that's the absolute value, and we did this so we wouldn't have the absolute value. So we're going to do a double chain rule. 1/2 x cubed plus 3 squared to the -1/2. And then we're going to multiply by the derivative of the inside. Maybe I'll change colors and do red for that. That's 2 times x cubed plus 3. But then we need to change colors again and multiply by the inside derivative of that. Oh, that's way too light. Sorry, I'm trying to be fancy here. I need like a dark green. 3x squared. So we did 1/2 u to the negative 1/2. Then we had to multiply by the derivative of u. And that's, u was like v squared. So that's 2v. And then taking finally the derivative of v is 3x squared. All right, there has to be some simplifying here. Let's see. The 1/2 and the 2 simplify. And I have x cubed plus 3 times 3x squared over the square root of x cubed plus 3 squared. Oof, man. So what we really have is x cubed plus 3 times 3x squared over the absolute value of x cubed plus 3. That's what we have.
Quick question.
Yeah.
I found on the internet that the derivative of an absolute value is just u over absolute u. That's what I've just been going with.
Okay. Yeah, well, the question when you have, and we could prove that if you like.
I don't know if that's always the case or is it just sometimes?
Yeah, so you'll see that we happen here. So if you have f of x equals u, the absolute value of u, then f prime of x, you can see that's what happened here. U over the absolute value of u times u prime. And you can prove that if you like. And the question for yourself is that a formula that's worth memorizing to me? It will always work, but is it worth memorizing or not? And I can't answer that for you. For some of you, like this is a crazy example and you're like, you know what, if this ever comes up again, I'd rather just memorize this formula. For others, the process that we did here was manageable and it would be better to just remember the process. So whenever you have a special derivative formula like that, it's all a question of, is it valuable to have that formula? It is true. It is a valid formula. So there's nothing wrong with that at all. And you can see that's exactly what we got. X cubed plus 3 over the absolute value of x cubed plus 3 times the derivative of x cubed plus 3. So yeah, it's true. The key here that I wanted to note, this x cubed plus 3 over the absolute value of x cubed plus 3, that's either 1 or negative 1, depending on whether x cubed plus 3 is positive or negative. If x cubed plus 3 is positive, then it's positive 1. If x cubed plus 3 is negative, then it's negative 1. Let's see if we can continue here. F prime of x, I'm really interested to get to the end and graph this one. I think it's going to be a funky graph. We're going to set it equal to 0 or see where f prime of x does not exist. Be careful with the 0 here. You might say, well, that's x cubed plus 3 times 3x squared equals 0. But in fact, what happens if x cubed plus 3 is equal to 0? So it feels like what we did, where we set the numerator equal to 0. We did one like this before. I think it was the previous one. And, oh, go ahead.
You get x cubed equals negative 3, and then you divide, you cancel out the cube 3.
Yeah, but there's another important issue that's happening here. I want you to look back, not just you, Christopher, but I want everybody to look back at the derivative here. And so what happens if x cubed plus 3 is 0? The derivative is not actually going to be 0. What happens if x cubed plus 3 is 0?
It'll be 3 times 3 x squared over 3.
No, not if x cubed is 0. If x cubed plus 3 is 0.
It will be 0 over 0.
That's right, Sandra. It would be 0 over 0 because the x cubed plus 3 is in the numerator and denominator. So this is a weird one. If x cubed plus 3 is equal to 0, that actually belongs over here. That means the derivative doesn't exist because it's 0 over 0. The derivative doesn't exist there. And then Christopher had started solving that. That's correct. X cubed equals -3. So x is the cube root of -3, whatever that is. So at that point, the derivative actually doesn't exist. And the derivative is equal to 0 when x is 0. So that's easy enough. Oop, no, I guess that wouldn't hurt anything. All
I
right.
have a quick question.
Yes.
Could you just explain again, I think I might have just blanked out for this part, why you didn't do the denominator? Like why that doesn't matter?
Right, yeah, usually it would. And so we started with the numerator and we said, well, we want to know when the derivative is 0. That's when the numerator is equal to 0. There's two factors there. So it could be x cubed plus 3 is equal to 0 or 3x squared is equal to 0. But then it's like, hold on. If x cubed plus 3 is 0, we're going to get 0 over 0. So that's actually the same as when the denominator is 0. And so it kind of moved over into the denominator not being 0 part of the analysis. So it actually, because it's in both, it kind of dual purposed. And we realized, hold on, that's not going to be a 0 when x cubed plus 3 is going to be 0. It's going to be an undefined. I don't know. So that's why. Was that?
Okay, thank you. That makes a
Sure.
little bit more sense.
A little bit more. I think that was an honest answer. It makes a little more sense. It's not, this is, like I said, this is a weird one. I think we need to see the picture when we're done to make it all come together. Okay, so I'm going to mark a negative cube root of cube root of -3 and 0. And so I'm just going to pick a big negative number like -10. Let's see. Cube root of -1 is -1. So this should be more negative than -1. So I should be able to do -1 here and then like 10 over here. And you can do different numbers if you want. Okay, so we're going to test these in the derivative. -10 cubed plus 3 times 3 times -10 squared over the absolute value of -10 cubed plus 3. Well, the 3 times -10 squared is always positive. The denominator is always positive because it's an absolute value. So then -10 cubed plus 3. Positive or negative? What do you think? -10 cubed plus 3.
Negative.
Yep, you're correct. That would be negative. So it looks like the whole thing's negative. So it's decreasing here. Then -1, f prime of -1, -1 cubed plus 3. 3 times -1 squared over absolute value of -1 cubed plus 3. Let's see, -1 cubed is -1 plus 3 is 2. So that's positive. 3 times -1 squared is positive. And in the denominator, that's absolute value, so that's always positive. So that's positive. And I'm assuming it changes direction, maybe not. F prime at 10. 10 cubed plus 3, that's positive. 3 times 10 squared, that's positive. Absolute value of 10 cubed plus 3, that's positive. So everything, it doesn't change sign there, so everything stays positive actually. Interesting. Was our original function defined at 0? It was, right? So it looks to me like we would answer this way. So this one's a little, there's an additional layer of complexity here. I would say f is increasing on the interval negative cube root of negative 3 all the way to infinity. And that's purposefully including the 0. That's a little sneaky though, so I'll let you think about that. And it's decreasing on the interval negative infinity up to negative, oh no, not negative, sorry. It's already negative. Cube root of negative 3. Too many negatives. It is a negative number, but it should just be cube root of negative 3. Well, I'm nervous. Let's see if we'll come back. Let me graph it, and then we'll come back and answer questions about that one. All right, y is equal to, and I think I can just do absolute value. Yep, x cubed plus 3. Whoa, weird. Incidentally here, let me do another graph for you. Y is equal to x cubed plus 3. So do you notice that they are identical to the right? Let me see if I can make it a little bit thicker here. A bit easier to see, maybe change colors. So it's like purple over here on the right because the red and blue are identical, but then they split, the red goes down and the blue goes up. Does anyone know why the blue with the absolute value here does that? Why it flips up like that?
Because absolute values are always positive, so it's always going to be up.
Yeah, you're right. All the red negative numbers here got flipped up to be positive. And technically we say it's not that absolute value is always positive, it's that it's never negative, because technically it can be 0. It's like a small technicality there. But and this, do you see this negative 1.442? Do you know what the exact number is for that? It's written on your page many times.
Is that the cube root of negative 3?
You are correct, Lorenzo. That's exactly it. That's the cube root of negative 3. Cube root of negative 3, negative 1.442. Isn't that cool? Oh, I love when like everything like backs up what we did. I'm like, yes, we had it right. So last question for you, and then we'll see if you have more questions. Why did I include 0? It's on the number line that the derivative is 0 there. But I included it and said it was still like increasing there. Seems like I'm like contradicting myself there. Any ideas on that? Okay, I didn't think so, because it's a weird question. Let me go back. Oh no, I did go back. So what we have for that part of it, just that part of it, it comes up, flattens out, and then goes up. So the key is, if you look to the left, this point is above all the points to the left. All the points to the left are below it. And this point is below all the points to the right. They're all above it. So it is above all of these points, below all of these points, so it's still increasing. Even though the derivative is 0 there, it's still technically increasing because it went up right before it and it went up right after it. So if you ever have a number line on a derivative chart, you have some c here, and say it's negative before, negative after, and it's not a vertical asymptote, like there's an actual point there, you can say it's decreasing and you can include, like this one would be negative infinity to infinity. You can include the c. It's a little subtle, but you can go ahead and include the c. Boy, we had a great day. This was a lot of good examples. You know, I had extra examples prepared, and I think we really did almost all the stuff that I wanted to do. So I'm gonna, where it's 10:35 already right now. So I'm gonna let you go and call it a day. For Tuesday, you should be watching the first few videos in section 4.4. And I would actually encourage you to maybe watch all of 4.4. So you're kind of ahead of the game, because we'll have 4.4 and then a little bit of 4.6 as well for Thursday. So it's a lot to do. So if you want to maybe knock out all of 4.4 for Tuesday, that would be good. And then immediately after class here, I have a news post updated that's going to come up, and that will have the quiz attached to it, and that'll be due to the Dropbox by the end of today, anytime by the end of today. Does anyone have any questions about the timing of anything? Any questions about what's due when or anything like that?
So the quiz is due by the end of the day?
Yep, by the end of today.
Okay.
Yep.
Is that a green screen?
So it's, I have a whole backdrop, but I don't have an actual, green screen yet.
Oh, good.
So it's not quite as effective. I have a green screen on order.
Oh, okay. Oh,
So I'm trying to have some fun, you know, and get the virtual backgrounds to work.
How do you even change the backgrounds?
If you click on your video, like if you see the little stop video, there's a little arrow next to it. And if you click on that, there's a virtual background setting. And then and yours should work, Chantel, because you have a nice solid background. So yours should work really well. It should be perfect. It'll probably be better than mine, because I have like my computer over here. You can see, and like the edge of the bars, it's just the room I'm in, like that stuff shows. But yeah, it's kind of fun. So yeah, that's it. And you can upload your own images if you want to put those as your background. So, okay. I think that's it. Oh, maybe not as good as I thought.
No. Gray doesn't work.
No, the gray doesn't work. I actually have a light that has to shine right in my face. Here, let me turn off. In order for this to work, I have to shine a light right in my face to make sure that I am bright enough.
Well, I keep hopping in rooms in my house because I have to share between homeschoolers, my husband working, and the baby to get quiet. So I'm kind of getting to see my house throughout the rest of the school year.
The room will change from day to day, huh?
Yeah.
Yeah. All right, everybody. That is it for today. Again, look for a news post with all the details, and email me if you have any questions. There have been some good use of the Discord chat. I appreciate that. Thanks to Haley for giving your tips about using the iPhone. That was super helpful. Yeah, that's it. All right, everybody. Enjoy the rest of your Thursday and your weekend, and I will see you Tuesday, if not before.
The quiz would be uploaded again?
10:40.
Okay, thank you.
Yeah, it'll be up there in a second. All right. Bye, everybody.